Hi guys, I want to show you how to make a simple model of a fiber inside a matrix. So let's do it together. So first let's open the abacus, press shift and right click and then open command window from here. So if you do this, it will open command window from this folder, session 1. Type abacus CAE. Okay, and then the abacus CAE window will pop up. So this is the model that we want to do. We're going to use the abacus 614. So there will be a cube of a polymer matrix with this size, and the fiber is a glass fiber with this property, the Young modulus, the Poisson ratio, and also this is the Young modulus of polypropylene, and this is the Poisson ratio of the polypropylene. We will discretize them with a solid element, 8 nodes hexahedral elements. And for the boundary condition, we will apply a constant, uniform strain along the boundaries following this Hill-Mandel kinematic. And then we will use the static solver. So this is the abacus welcome screen. So just click here and enlarge the window. Hopefully you can see these windows. Click here, create part. So what we are going to do is that first we need to create two parts, one part for the matrix and one part for the fiber. So let's do it for the matrix part. Click continue and then click here. From here 0 is 0.0 and then you type 21.1 comma 21.1 and then click here. No, click done, and then the depth is also 21.1. So this is the matrix part, and then we need to create another matrix, the fiber part. The size will be, let's say, 8.5. Click here and make a dimension for the radius 8.5. okay, and then click here 1 and then click done, and then for the depth with the same depth with before, 21.1. So now if you click here, this is the part. We have a matrix part and the fiber part. So what we need to do is to combine these two parts into a new part, which is the union of these two parts. How we do that is basically we need to go to the assembly, because we need to assemble these two things. So click here, create instance, click and shift so to choose both of the parts, and then click OK. So this is what you have, but this is now the fiber is mispositioned, so you need to translate the fiber so that it is located right in the center of the polymer cube. What you need to do is to click here, translate instance, and this is the translation coordinate. You want to translate from 0, 0, 0. Just click enter, just press enter, and then type you need to type 21.1 divided by 2 is 10.55, I think. 10.55, 10.55. Okay, and then click enter. See, now it's right in the center, and then click OK. Now these two instances, the fiber instance already located very well, but these are two separate instances actually, so you need to merge them to form one union. So what you need to do is click here, merge or cut instance, and then this is just name it union part. So you want to merge the geometry, and the original instance we will just suppress them, and we want to retain the boundary between these two instance, two parts, so that we can assign a different material property later on. So just make these options and then continue, and then choose these two things and click done. So now they are become. So if you go to module part and you go to this selection, part selection, you will see this new part, union part. So the next step is go to property, create a new material for both of them. So we need to create a PP material, and then click here mechanical elastic, and then the Young modulus for the PP is 1.7 GPa, and the Poisson ratio is 0.4. Click OK. Now click again for the second material. Now this is the glass fiber material, and click elasticity. The Young modulus is 72 GPa with the Poisson ratio of 0.22. Alright, now we create the section for that. First we create a PP section, and then click, and then choose also the material should be PP. So the section PP, the material is PP. Now create the new section. This one is the GF section, and the material is the GF material, and then we will assign both of the material property to the corresponding part. Assign. Here we choose this one, and then make sure you change the name of the set, GF set. Okay, click OK, and then section, choose the GF because this is glass fiber. So see, the color change means that you already assigned a material property there. And then you want to assign another one, click here for the matrix, change this to PP set, click done, and then choose from this section a PP section and click OK. And we only have two, so it's enough. Click here, cancel procedure. If you want to check, you can just change this one, the color, the material. Click here, because they have different material, they have different colors. And then click here to step. So this is just to set up the analysis setting. So click here, create step. We are going to use the static general using the implicit. If you want to use the explicit, you need to choose, for example, this dynamic is explicit, but we are going to stick to this one for now. Continue. And because this is going to be a very small deformation, we will just to turn off the nonlinear geometry, and the time period is 1 because this is not rate dependent model, so it doesn't really matter what time you put here, so just put 1, and then click OK. And then this is just for the sake of the input, so make here I want to make the output field every 10. I want to make a 10 output files. So from 0 to 1 is the simulation time. So each is it's 0.1 second you will output the result. So this is important from this is because we want to do homogenization later on. So make sure, because the homogenization is the idea is that you average the stress and the strain over the volume. So in order to do that, you need to know the volume of each integration point. So make sure you tick this option, IVOL, integration volume point volume, and then click OK, and make sure you click the stress and the strain. Maybe we don't need the context, so you can remove it, or click OK. And then go to the load because we want to apply the load, right? So we want to make a constant strain, a uniform strain along the boundaries of this RV. So this is the equations. Where is the equation there? So this is the equation. So this is the general Hill-Mandel kinematic boundary conditions. So the final, if you, for example, if you want to pull in the x direction, means the EXX is 1 while the rest are 0. So you need to set the UX, the displacement in the x direction, equals x, and the UY equals 0 and the UZ equals 0. How will we do that? So let's put it here, and how we do that, so click here, create boundary condition, click displacement, make it a BC1. BC1 is a UX. Okay, so for the set, we just change the set name, boundary set. So here we need to select all the surface, so make sure you choose these faces. So click here the faces one by one and press shift to select more than one faces. If you want to rotate, you can press Ctrl and Alt and then rotate. So now everything has been selected, I think, right? Every face is on the mirror. Click done here, and now we want to make the UX, the U1 here, because we want to apply the UX. So now UX equal 1, but now you don't want to make a uniform distribution because you want to make the UX equals X. So you need to create equations for that. So you click here, create analytical field for that, and click continue, and click here. This is the X coordinate. So click OK. But after that, make sure you change the distribution to here, analytical field 1, and then click OK. So you can see here, because if you don't change it, for example, if you do it uniform, you can see from the arrow that there will be a uniform strain of uniform displacement of 1 through the boundaries. But that's not what you want. What you want is that you want to have a constant strain, so the displacement will be from 0 to 1. So you click this one, and then you can show here. So there is a 0 displacement in these faces, but the 1 displacement here in these faces, on these faces. And then you need to create for the X and Y coordinate. For the X and Y, it's quite easy because they are both 0. So what you need to do is just click continue. And the set, we don't need to create a new set because we will apply it to the same boundary. So the set is already available. Click sets here. Click boundary set and continue. But now click UX equals 0. And then create again for the third thing. Continue, boundary, and now U3 equals 0. So that's it. So now we did everything. What we need to do the last is to assign to make a discretization, to meshing, to do the meshing. So here, okay, so if there's a warning say that dependent part instance cannot be edited or assigned mesh as attributed. So what you need to do is to go to part and then click here. And then this is so the abacus recommend you to mesh it with a 2.4 unit length. I want to decrease it 1.2, and then click here to mesh it. See, now it meshed. If you want to make the size of the mesh smaller, you can make it smaller number. So okay. So now if you want, for example, oh, I don't want to use the hexahedral mesh. What if I want to use the tetrahedral? So what you need to click is here, assign mesh control. And then you need to click here to drag here. And then yeah, because we already mesh it, so basically the idea that okay. And then you can also change hex dominated. Hex dominated means that the model will contain several hex and then several tet. And then if you want to fully tetrahedral mesh, click here. For example, we delete the mesh, then click here. Yes. So we will have a tetrahedral mesh. But for now, let's stick to the fully hexahedral mesh. Click here and then click OK. And then click here again and click yes. So now you want to this is a hexahedral mesh, but the hexahedral mesh can be linear element or quadratic element. So this is how you assign the material, the element type. Click here. We want to assign for both of them, so click. If you want to choose, if you want to select more than one, press the shift and then click, then go to continue. For example, if you want to use the quadratic element, you can click here, or if you want to use linear, you can click here, or depending of there are so many element formulation, you can click hybrid or whatever. But for now, you use the reduce integration to increase the accuracy. Click here, so we use the second order accuracy. Okay, and then click OK, and then dismiss, and then done. So that's it. We already meshed it. Now we can submit the job to the ABAQUS solver. So we need to go to here, the job, then we click here, create the job, single fiber. Okay, and then click continue and click OK. Then you go click here, the job manager. So there is one job named single fiber based on the model number 1. The type is the full analysis, but now we haven't submit, so we need to click submit. So now the status is submitted. Now it's on process. It will change to running, means that they're now solving the problems. Shouldn't take a long time. You can also monitor the progress by clicking monitor here. See, it will tell you what step, what increment, how many equilibrium that it takes to solve, and now it's already finished, I think. Dismiss, and then if you want to show the result, you click result here. If you click here, it will open automatically ABAQUS viewer, and then it will show the result. Click here. Okay, see, so this is the result. So basically you've just solved the single fiber in a matrix problem. So what we are going to do next is basically we have the stress and the strain distribution in this RVE. We want to average the stress and the strain to get the macroscopic stress and strain, so that we can construct the effective stiffness matrix at the macro scale, so we can calculate the eigenvalue, which will be the content of the next video.